this is this does not seem to be on. Oh, hang on. All right, that better. We can hear something. Okay. So today is the last sort of lecture of actual course content. I mean, of course, there will be a lecture next week on Monday, which is the revision lecture, where we'll talk a little bit about the final exam, but mostly we'll be trying to answer questions that you have. So if you haven't seen it, there's a post on Piazza asking you to ask questions that you want to have addressed in the revision lecture. So if you have any particular questions or topics that you want me to bring up in the revision lecture next week, please reply to that thread, or if you post a different thread, make sure you clearly mark it as a revision related. Also, I don't suppose I have to remind you that the due date for assignment 2 is today at the end of the day, and that presentation recordings are due on Monday next week, and then the presentations will happen during labs next week. So in order to be able to run all the presentations in the labs, in the on-campus labs, we have booked some additional rooms, so we can't do, in the big lab, we can't do 60 presentations in one room in one lab, so we're going to split the groups. But you shouldn't have to worry about that. We'll make sure that someone is there in the lab room at the start and gives you instructions on where to go if you need to go somewhere else. And it's going to be within the same building, so it's not a problem. All right. So the topic of this lecture is threads or concurrency in, well, in programming in general, but in Java in particular. So first of all, what is concurrency? What do we mean by concurrency? Well, concurrency is when multiple things are happening at the same time, or even appear to be happening at the same time. So this is quite common on, at least on modern sort of computer systems, where you have a lot of different things going on at any one time. So for example, this computer here is currently displaying slides. It's running the streaming, and it's of course has the IntelliJ IDE open as well, although that might not be doing anything at the moment, but it's still kind of a concurrent process running on here. But before we sort of talk more about concurrency in a programming setting, I thought, well, let's see if we can think up some examples of concurrency and how it's implemented in sort of real life. So can anyone give an example of something that is sort of concurrent that has nothing to do with computers, or that is concurrent in normal life? Well, yep. Sorry? Yeah. Yeah. You mean that you're doing multiple things in the kitchen at the same time? Yeah. Yeah. That's a pretty good one. In fact, yeah. I think that one is a good illustration of the second point. But just to say, the sort of general thing about concurrency in the world is rampant. I mean, it's everywhere. Someone is walking over there while I'm talking. These two things are happening concurrently, right? So lots of things are happening at the same time. Now, the example that was given relates more to the second point, which is time slicing. So, of course, modern computers, you often have multiple CPUs in a computer, which means the computer can actually do multiple things at the same time. But on sort of simpler or older computers, you have only a single CPU. But even a single CPU system can do things concurrently by switching from one to another. So at the sort of micro level, of course, if you have a single execution unit, which means a single CPU or indeed a single human, maybe you can only really do one thing at a time, but you can be engaged in multiple activities at the same time and switching between them, right? So in computer systems, this is called time slicing or time sharing. So the cooking example that was given is a good one because you have multiple sort of threads of activity going on in the kitchen at any one time. Of course, you're only actually doing one at a time. Like, you know, you're chopping the carrots, meanwhile something is simmering on the stove. Every now and then you have to switch back and forth, go and check what's happening over there, then come back to chopping some more, and so on. But you still have this sort of concurrent threads and a single execution unit, that is you, keeping sort of dividing your attention or your time between the different threads, right? So in a computer environment, when we talk about concurrency, we also distinguish between processes and threads. Well, I might be using these terms a little bit loosely, but they are sort of more precise. The terminology might also vary a little bit between different operating systems or different computer systems. But at least on a sort of Unix and its derivatives, a process is something that is what's called a separate execution context, which means that sort of by default, at least, two different processes don't share anything. They're sort of independent. They might be even unaware of each other's current existence. So an example of that would be that for example, the IDE that is running here and the PDF viewer that is showing the slides are completely separate. They're unaware of each other's existence. They don't talk to each other in any way. If you want processes to somehow interact, you have to set up some kind of mechanism for that to happen. So there are, depending on your system, or your operating system or your computer system, there can be many different ways in which processes can interact. So, for example, you could say that the PDF viewer and the streamer here are kind of interacting in a roundabout way, because the PDF viewer is showing things on the screen and the streamer is grabbing what is shown on the stream and sending that off somewhere. So they are interacting through this kind of shared resource, which is the frame buffer that is showing contains what is being shown on the screen. Now, threads, on the other hand, are concurrent activities that are happening within a single execution context. So, and instead of using a fancy word like execution context, we might say running program. So within a single running program, we have multiple threads. And because they're within the same process, within the same running program, they share things. So in particular, they share memory. So the memory that one thread is using is the same, or can be the same, as the memory that another thread is using. When you do threaded programming, and particularly if you do it in Java, multiple threads can be executing the same methods. And indeed, they can be executing the same methods on the same objects. And this is both sort of a benefit and a curse, because on the one hand, if we don't have this kind of interaction between threads, well, in most cases, the threads would be pretty meaningless. So when we use concurrency or threads within a program, we're using it because we want different threads of activity to be interacting, to be solving some kind of overall tasks together, right? And we'll talk about some examples in a sec. But on the other hand, the fact that we have these independent threads of activity that are all operating on the same code, the same data, is what gives rise to all of the complexities of concurrent programming. So we'll mention race conditions a little bit later, which is kind of one of the big problems of concurrency, and that happens because we have threads that are accessing the same data, right? Or accessing reading and writing. All right. So why are we interested in multi-threaded programming, or indeed anything in concurrency? So I guess the main reason why we would do it within a program is what's described as separation of concerns. So again, sort of coming back to what's currently running on this laptop. So the reason why we want to be able to run things in parallel is because we want to be able to do things like display slides and run the streamer at the same time. We don't want to have to go and write a custom program that does slide display plus streaming as one integrated unit. So even if we have to do it by time slicing between two processes, in this case, it's from a development perspective, it's much easier to write two separate processes, have a framework that handles the division of time and responsibility between them, rather than having to sort of write custom code for every possible combinations of tasks you would like to do concurrently. Another example would be, for example, I don't know if any one of you have in your game implementation used animations or sounds, but let's say if you have a game that is playing a background soundtrack while you're playing it, then you would probably want to have separate threads. One is responsible for playing the soundtrack, and the other one is responsible for handling and responding to player actions, right? Now, you can make a distinction between concurrency and parallelism. I'm not sure if this particular way of slicing up the terms or using the terminology is really standard, but when we think about concurrency, you often probably think about using multiple processors to do something faster. So here we'll label that as parallelism as opposed to concurrency. So concurrency is more about, in general, when we want to do things at the same time, even if it's not really at the same time, it might be time sliced. Whereas parallelism is when we really want to use parallel execution, and typically we want to use parallel execution to do a task more efficiently, or let's say faster in terms of actual wall clock time than we could if we were doing it on a single CPU. So in order to do parallel programming, we need to have parallel compute resources. It could be multiple CPUs on a single computer. It could be in a bigger system, it could be multiple computers that are chained together in a network. So this is sort of used for, computationally intensive problems is a bit of a misnomer, because in some cases, so you can think of sort of big computations where you want to slice up the computation in order to solve it faster, but there are also cases where you do some sort of, I guess, any sort of streaming or where you have multiple tasks that are sufficiently compute heavy and time critical that you need to have them on parallel hardware. So a good example of that would be any sort of control system. So for example, if you take a modern car, you have somewhere on the order of probably a couple of dozens of computers distributed throughout the car. Right, and each one of those is doing some job, like for example deciding whether or not it should apply brakes. That's a scary thought. And those are running in parallel because one, it would be, from a design point of view, it would just be cumbersome to centralize all that execution in one computer, and also because most of those things are time critical, which means that if you have a dedicated computer that is handling something, you have better control over the timing, which means you can sort of guarantee that whatever runs on that computer will run fast enough to respond within the time that you have decided is sufficient. All right, so with that as a sort of just a general introduction, let's talk about threads in Java and a little bit of examples of how you can implement them and what can happen. So Java is, I think, a language that was designed to deal with concurrency sort of from the bottom up. It's not an extra thing that is added on. It really is embedded into the language. You wouldn't necessarily see it everywhere. I think you can see it if you look at something like processor usage when you're running Java programs, because the virtual machine that executes a Java program, at least in some cases, will actually parallelize the execution, even if you haven't done anything particular in your program to make it parallel. But if you specifically want to implement threading in a program, there's in the basic Java Lang library or package, there is a class called thread, which is sort of the base class for all threads. And there's two different ways that you can implement threaded code. So one is that you subclass thread and you override the run method. So the run method in a thread class is what actually gets executed when the thread is running. And the other one is that you can use an interface that is called runnable. So there are sort of two ways that you can initialize a thread. Either you have subclassed it and overridden the run method, in which case your overridden run method is what will get run, or the sort of default thread class, if you provide it with an object that is runnable, then when the thread is run, it will call the run method on that runnable object. So this has sort of, I guess the main implication of these two different ways of doing things is the distinction between threads and objects, right? So if you subclass thread, then there is sort of a one-to-one correspondence between threads that are running and instances of your subclass. So every time you want to start a thread, you will create a new instance of your subclass, which provides you with some kind of encapsulation. Like, for example, if you wanted to store, say, an identifier, a number that belongs to each thread that you start, you would naturally do that in your subclass. With the other method using runnable, well, then and we'll actually use this in our example in a sec, well, you could instantiate multiple runnable objects and provide each thread with a separate object that is running, but you can also provide the same runnable object to multiple threads, which is, again, coming back to this point that when you're running thread or writing threaded code or running threaded code, often you will have a case where multiple threads are executing the same methods and even the same methods on the same objects. And again, this is necessary if you want your threads to coordinate in any way, to do anything sort of jointly rather than just doing things all on their own. But it's also a source of complexity, because this is where we run into all the sort of coordination problems with threaded programming. So just as an aside, if you subclass Fred, well then of course your subclass has access to all of the Fred operations, which aren't that many. If you use the runnable interface, well then how does your code know what Fred is currently executing it? Well, maybe you don't need to know, but if you do, there's a static method in Fred called currentFred, which returns to you the currently executing Fred. So we'll see in our example how this works. All right. Actually, let me take a step over here and see. This is just the API documentation for the Fred class. You can look this up. Notice that at least in the current version, there's a lot of methods here that are labeled as deprecated. This means that they are going to be removed in some future edition of the Java standard library, and you shouldn't use them. Probably because they have some kind of problem that designers didn't think about when they first introduced them, but have now realized, and therefore they will be removed. But if you look at what you can actually do with a Fred, it's not that much. You can, let's see, you can start it, you can run it, you can do things like get name and get ID, so every Fred has a name and an ID. You can, when you create a Fred, you can assign it a name, it's a string, or you can't assign it an ID, I guess that's assigned automatically. There's also the concept of a Fred group, but we're not really going to go into that. That's sort of a collection of Freds, and you can do some things jointly with all the Freds in a Fred group. As I mentioned, you have some static methods, like currentFred is probably the most interesting one, which returns the Fred that is currently executing. You can ask for the Fred state and a few things. Now, if you read this a bit more carefully, notice that there are some methods here like stop and suspend, but all of those are deprecated. So in fact, if you look at this more carefully, there is, at least in the Fred object itself, there is no way that you can sort of just kill a Fred. I'm not sure if you can actually, maybe you can do that through Fred group, but so generally what you can do with a Fred is to start it and then wait for it to finish. So if you call start on a Fred object, that will start execution of the Fred. And as I mentioned, the run method in the Fred class is what actually gets run when a Fred executes, which either is your overridden implementation, or it is it will just call the run method on the runnable object that you provided to it when you constructed it. The other thing, as I said, you can start it and you can wait for it to finish. And the wait to finish is called join. So if you call Fred, or if you call join on a Fred, what that will do is pause the execution of the current Fred. So that's not the one you're calling something on, it's your current Fred, until the other Fred that you call join on has finished, and then come back to the one you're currently executing. So actually this is a very interesting question. Let's look at join. Wait for Fred to die. Yeah. Okay, it doesn't say. I actually have no idea what will happen if a Fred calls join on itself. Possibly it will just do nothing. Possibly it will just completely hang the Fred and it will never finish. I don't know. We could implement a test and try it. But let's try our other tests first. So let's look at a test. So here is a simple sort of basically a nonsense implementation. It's not going to do anything in particularly interesting, but it will just demonstrate some of the things that are happening. So here we're using the runnable interface. So we have defined a class that implements runnable. And as I said, the runnable interface has to have a method called run. That's the only method in the interface, and that's the one that will get executed when this runnable object is run, right? So what is this runnable object going to do? Well, it's going to access a counter. So we have this counter called work item. So the idea of this class is that we want to sort of simulate the case where we have some number of workers. We call them workers typically because they're doing work. And we have a list of tasks that need to be done, and the workers are just sort of greedily going to go and grab the next available task, work on it until it's done, and then go and grab another one. So essentially this is what we would previously just described as parallelizing parallelizing the implementation, or parallelizing a computation. So in this case, we have said here that we have 1,000 work items to do, and each work item is just identified by a number. So what the run method here will do is just to grab the next available work item, which is there's a little utility method here which called inc work item, which just returns the current value of this work item counter and increments it by 1, so that we have sort of given the next task to the one who's requesting it. And so they're going to keep doing that until we run out of work items. And then they will just call a method here called work hard on the work item. So the worker will just do some work. It doesn't really matter what it's doing. Here we'll just do a very stupid implementation of checking whether or not the work item is a square. But this is just sort of burning some CPU cycles in order to illustrate what is happening. But let's say that this is a simulation of the worker doing some kind of intensive computation, right? Now, what else? And then each worker will also count how many tasks they have done. So this my tasks here is a local variable. It's local to the method, so it will just get sort of incremented within the method, and then at the end, when the thread is done, it will say how many tasks it has done. Right. So notice here that we're using this thread.currentThread, because the way that we will instantiate this is we will have a single workers object, right? Which and then we'll have multiple threads all running the run method of this single object. So in order to know which thread we want to print something for here, so to identify it, because this code will get executed by all the different threads. So we can't have sort of a variable or a field or something in the object that identifies the thread here, but we can use thread.currentThread to get the current thread, and then we can use getName to get some identifier. Question? Well, that's what current thread tells us. So, oh, how does that know? I have no clue. But this is something that is hidden somewhere in the implementation machinery. So, just to repeat the question for in case it wasn't audible. So the question is sort of how does current thread know what is the current thread that is running this code? So there is something that is called the scheduler, and so this is part of, in case of Java, of the Java virtual machine. when you have, if you talk about operating systems and multiple processes running on a computer, there's also somewhere in there's a scheduler that is allocating runtime to on the different CPUs, if you have more than one, to the different processes. And the same with the Java virtual machine. The scheduler is the one that sort of controls which thread is getting executed at any one time, including on multiple CPUs or on a single CPU, depending on what's available to it. So the scheduler would sort of have an idea of what is the current thread that is running, and I guess that information is somehow passed into the thread object so that it knows what it is. But yeah, so I guess another way to answer the question is to say that, well, the thread infrastructure or the thread class in Java allows us to abstract away from that, so we don't have to know. But again, coming back to the previous discussion about the two ways of implementing threads, if you wanted to keep track of this yourself, you could use the other method of implementing threads, which is to subclass thread. And then your subclass could store some sort of identifier, and because then you have this one-to-one correspondence between instances or objects that are instances of your subclass and running threads, then every object that every one of your thread objects would know which object it is, right? You would have essentially a correspondence between the this and the thread. But here, because we're running multiple threads on a single object, we don't have that explicitly, and we have to rely on the thread infrastructure to tell us what is the current thread. It is a bit of a bit mind twisting. This. All right. So one of the reasons why we implemented it this way is because, so as I said, we will instantiate all these threads with a single object. And the reason why is because we do want them to share something, right? We want them to share the work item counter. Because remember that the setup here is that we have this list of 1,000 tasks to be done, and we want to make sure that each thread is grabbing the next available task. If we had separate work item counters for every thread, all of them would just do 1,000 tasks, and it would be completely redundant. Of course, we could do some sort of a priori division where we said you do the first 500, you do the next 500, but that's also a bit wasteful because the first, well, actually, the way this work hard function is written, the first 500 are going to be finish faster than the next 500, right? Just because it's doing a loop up to the current work item number. So the higher numbered tasks are going to take more time than the lower numbered task. So the work item counter, which is this one, which is sort of our simulation of a list of tasks to be done, is a field in the workers class, right? So this one is now shared by all the running threads. On the other hand, this myTasks variable, this is local to the running thread because it is local to the run method. So I'm not sure to what extent we covered this in detail in the beginning, but the work items field will be allocated on the heap somewhere, whereas the myTasks variable will be on the stack, right? So every thread will have its own stack, but they all share the heap. All right, so in the main method here, what we're going to do is just, well, we create a workers object because that's what we need, and then we create an array of threads, and we initialize every element in the array by a new thread, and we pass this workers object as the runnable object that this thread will execute, right? And we also give it a name here, which is just worker plus index. And then we just start all of the threads. And then at the end, we'll print out just something so that we know when the main function exits. All right. so let's see what happens. Actually, let's scroll back up and have a look. Okay, so there's two parameters here: the number of work items to be done, and the number of workers or the number of threads that we are going to be running. Right. So here we've set it to something very simple. It's 1. So we're just going to start a single thread, let that thread do all the work while the main thread is just sitting idle and waiting for the other one to finish, and then printing out, oh, it's all done. Okay, so let's run this. And what we can see in the output is two things. Well, first we see that worker 0 did 1,000 tasks, which you would expect because there's only one worker and there's 1,000 tasks to be done. That's all good. The other observation here is that the all done is printed before worker 0 finished. Right. So, and the reason for that is that we just started a thread here and then we printed out all done. Right. So we didn't actually wait for this thread to finish. We just started it and then finished the main method. And the program keeps running until all the threads have finished, and eventually the single worker thread finishes and it prints out this final message saying it's done 1,000 tasks. So in order to wait for everything to be done, what we need is something like this. I don't know if we actually need that try-catch block, but so remember I said that you can't really stop a thread, but you can wait for it to finish. So what we do here is just for all the threads that we have started, we now call join on them. And what join does is to pause the main thread that is just sitting here and doing nothing until those threads have finished. And you might notice here that we're actually waiting on them sequentially, right? So first we're waiting for worker 0 to finish, and then we're waiting for worker 1 to finish, and then worker 2, and so on. But of course, all the workers are running in parallel, and if they're doing approximately the same amount of work each, then we would expect all of them to sort of finish at the same time. So we would probably expect that here we'll be waiting for a while for worker 0 to finish, but then once worker 0 has finished, the other ones are probably already finished or very close to finishing, which means that the next join calls are going to be waiting for a very short amount of time. So if you call join on a thread that has already finished, it should return immediately. We can also put this thing here so we can see what's happening here. So here again we're using current thread, but notice that we're using current thread in the main method here. So all execution in Java is happening in some thread, right? So even when we run just a normal single-threaded program, there is a thread that is executing that program, and we can use the current thread method to sort of find out what is the thread that is currently executing. All right, so let's run this and we'll see what happens. All right, so here we see that the name of the thread that is executing the main method is main. Okay, so the main thread is idling or just waiting. Now the worker does all its work and finishes, and because the main thread is waiting for the worker to finish, we get the all done after the worker is finished. Right. Okay, so that's the basics of it. So now let's try this with a couple of more threads. Let's take 2. So here we see that we started 2 threads. The 2 of them did some amount of work. It's not a perfectly even split. One of them did 551, the other one did 472, but we waited for both of them to finish. Now, what does 551 and 472 add up to? Anyone who's good at fast arithmetic? It's not that hard. Sorry? 1023. Yeah, it's probably correct. I wouldn't be able to do it myself. But the key thing here is, how many tasks did we have to do? 1,000. How many have they done? Well, it's more than 1,000, because 550 plus 450 would be 1,000. So it's definitely more than 1,000, right? So they have done more work than there was work to do. Let's just run it another time just to see that it sort of wasn't by accident. This is definitely more than 1,000, right? 600 plus 400 plus something. So the workers are doing more work than there was work to do. So how is this happening? Well, it sort of has to happen because there is a duplication of work. So some of these tasks get done by both workers instead of just by one. And how does that happen? Well, so this is where we get to what's called a race condition, or more generally the synchronization problem with any sort of concurrent computation. So race condition is a term that is used for a situation where we have multiple threads that are sort of both reading or writing, or well, it could be just writing, I guess, a variable or any sort of anything in memory that they both access, they both share. And because we don't know and we don't control what the scheduler does, which allocates runtime to the threads, it's essentially non-deterministic, or you might call it even random, which one gets to read first, write last. Maybe when we talk about writing, it's more about who gets to write last, right? So if we have a time-shared execution, or even if we have a parallel execution of a thread can sort of stop at any time, and another thread can come in between and do something, and then the first thread continues. So if we look at what exactly is happening here, so when a worker thread wants to request a new task to work on, they call inc work item, right? Now, what does inc work item do? It uses the postfix increment operator, which, if I remember correctly, should return the current value of work item and then increment the current value by 1, right? So although this looks like it's a pretty simple little statement, it actually consists of multiple things, right? It will go and fetch the current value from memory, and then it will add 1 to that value, and then it will store the updated value back in memory, and then it will return the value before update, right? So that's kind of the sequence of steps that is happening just in this little return work item plus plus statement. And if we have multiple threads running, they can be sort of whether they're time sliced or actually running on parallel CPUs, they can be interfering or interrupting each other in this process at any point, right? So what we can have happen is that worker 0 goes and reads the current value, worker 1 goes and reads the current value, both of them add 1 and store back the updated value, right? So one thread can sort of sneak in, read the current value, while the other one is in the process of adding 1 and writing back an updated value. And that's how we end up with duplication of work here, that the two workers, even though we had just 2, managed to do some of the tasks, both of them, right? So Java provides a mechanism for, or rather, let's say Java provides a simple or highly abstracted interface to a mechanism that can take care of this, which is the synchronized keyword. So what is actually going on is that there is somewhere in here there is something that is called a lock. a lock is something that you can apply in concurrency. We talk about locks, and a lock is something that only one thread can hold at any time. So there will be a lock, and a thread can request the lock. If the lock is free or like currently unlocked, it goes to that particular thread, and the lock is set to locked status, and then no one else can request the lock until the thread that had it releases it. And the implementation of locks is done very carefully to make sure that these particular steps, like requesting and changing status to lock, are done in an atomic way. So atomic meaning that the execution of that step, or those two steps in the process of acquiring a lock, it cannot be interrupted by another thread, so that we don't have the same problem in the lock. But in Java, we don't have to worry too much about this, because, like I said, Java is designed to be a threaded language, so it has this locking mechanism already built into it. In fact, there are certain operations in the language which are implicitly always locked. So when I think, although I shouldn't swear to this, but I think, for example, when you run the class initialization code for a class, then that's an implicitly locked operation. So it shouldn't be the case that two different threads are both trying to initialize a class at the same time, because class initialization should only happen once, right? Not class initialization, not object initialization or instance. But you can also see this, the fact that it's a threaded language, in that instead of sort of using a library that provides lock mechanisms, we actually have a language keyword for saying that we want something to be locked. So we have a keyword called synchronized, which we can put on a method. So same as other keywords or modifiers like public, private, or static. So synchronized is saying that this method should only be executed by one thread at a time. So let's say we make this one synchronized. So if we make this method synchronized, this method should only be executed by one thread at a time, and that should take care of our problem. So let's try that. And what do we got? 469 plus 531. Okay, that adds up to 1,000, right? And we can run that again. 550 plus 450, 1,000. Try again. Yeah, again, 520 plus 480, 1,000. So, okay, this took care of the race condition. So now the two workers are sort of not duplicating tasks. Each one is doing, each task is done by only one worker. And we should see that this works also if we increase the number. Let's say we go to 4 workers. They should be, there's a bit of a difference in how much work they all did, but they should be doing about 250 each. Well, here some have done more, some have done less, but still it adds up, right? 235 plus 265 and 240 plus 260. All right, so let's push this a bit higher. Let's say, well, we want to have lots of people working for us, so we'll do 20 workers. And we'll see what happens. Well, what we can see here is that we're not seeing such an even distribution of work, right? So this guy did 300 something, this one too, and then there's a whole bunch of workers that did nothing. So let's run that again a few times just to see that it wasn't an accident. Again, we have 1, 2, 3, 4, 5. Only 5 that actually did something. Yeah, we have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. Only 4. Okay. 1, 2, 3, 4. Okay. So what we're seeing here is that even though we allocated 20 threads to do this work, only somewhere between 4 and 6 of them are actually doing any work. The other ones are just sitting there and presumably just waiting to get their first task. Right. Now, to some degree, this might be a consequence of the synchronization mechanism. So let's remove the synchronization for a moment and see if that changes it. Of course, by removing synchronization, we get back our over counting problem or our sort of duplication of work. But see, this also did not really change the fact here we have 1, 2, 3, 4, 5 workers that actually did anything. So it's not really because of the synchronization mechanism. So why is this happening? Well, as I said before, the way that sort of concurrency works, if you have more threads than you have actual execution units or CPUs, is by time slicing, right? And somewhere in the virtual machine there is, as I mentioned, a scheduler whose job is to sort of allocate time to the different threads. And the scheduler, at least as far as I know, in the Java virtual machine is a fairly sort of relaxed, nice guy. So it's not going to interrupt executing threads in sort of any hard way. It's not going to say, hey, you stop now, I want to give some time to this other thread. It will only interrupt threads when they actually have nothing to do. So what does it mean to have nothing to do? So having nothing to do in a threaded programming context usually means something like the thread is sitting and waiting for something to happen. So it might be waiting for input. A good example of waiting for input is in the graphical user interfaces in JavaFX, where you're waiting for the user to click on something, right? And your event handling thread, because there is a thread somewhere in there, is not going to actually execute or do anything until there is an event that it needs to handle. So while the event handling thread is sitting idle waiting for you to click on something, the scheduler is probably going to run some other threads. Other examples is if you're waiting for, say, input from a network, or if you explicitly say that this thread is going to go to sleep for a while. It's going to have a nap. Typically you would do that if your thread is managing some kind of process that is timing dependent. So for example, let's say if your thread is playing sound. Well, the way, now I don't know exactly how this is done in Java. I'm not familiar with if it even has a sound system in the standard library, but typically the way it will work is something like you will load a bunch of data into a buffer, send that off to whichever piece of hardware is actually responsible for turning bytes into sound signals, and then just wait for that buffer to clear. And then when it's done, you will load up another buffer, send it off to the sound system. So a thread that is doing that will typically be sleeping for a while in between each sort of buffer call. And there are other cases where, for example, you're waiting for input on a network or anything like this. So in order to get our workers here to distribute more evenly, we can try a couple of different things. So one thing, as I said, we can try to use the yield method. So I think it's described here in the thread interface. If we go down to the bottom, so you can see that the thread class has a method called yield, which is, the description is saying, a hint to the scheduler that the current thread is willing to yield its current use of the processor. So it's basically the thread telling the scheduler that, okay, at this point I would be fine with being interrupted if you want to run something else. So let's see if that changes what happens. Not that much, right? Still just 1, 2, 3, 4, 5. We got 1, 2, 3, 4, 5, 6. So it's still only about 5 or 6 that are running. Oh, actually, I should have probably mentioned one more thing before we ran this, which is, well, why is it 5 or 6? You know, why is it not just 1? Or you mean 6 CPUs? Yeah, it probably has 8, but I'm guessing one of them is completely consumed by running the streaming, and another one is probably doing some operating system stuff. So yeah, basically the Java virtual machine grabs as many CPUs as it can get its hands on and uses them to run threads. That's exactly correct. And this is just what we end up with. So so we can see that the yield didn't really do much. It doesn't seem to work in this context. And the reason here is that these threads are actually running stuff all the time, right? They're completely busy. They're grabbing, except for the only point where they're not busy is if they are waiting to get the synchronization lock. Did I put that back? Actually, yeah. So that's the only point where these threads will be waiting. Otherwise, they're busy all the time. They get their next task. They do this little loop, which is doing a bunch of multiplications, and then they get the next task. So they're not really, they're never idle except for waiting on that lock. And apparently that's not enough, not quite enough to make them sort of share the execution resources. So in order to change this behavior, we'll have to make the workers a bit more lazy. So instead of actually doing any work, instead of sort of running the CPU, they're just going to be pretending to work. And pretending to work means they're going to go to sleep and have a 1 millisecond nap. So for every task they do, they're just going to go to sleep for 1 millisecond. And then we see a very different distribution. So remember, we have 1,000 tasks to do. We have 20 workers. So if everything is even, you would expect to see 50 each, right? And what we can see is that it's not perfectly even. Some did a little bit more, 51. 19 only managed to do 47. But it's fairly close to an even distribution. So here, because the threads are spending most of their time just being asleep. I mean, in the scale of execution of simple code like this, 1 millisecond is a long time, right? So they're spending most of their time just sleeping, which means that the other threads get plenty of opportunity to run. All right. I think that sums up what we wanted to do with this lecture. So it's a bit shorter than the last one. So unless there are any questions on this or any other questions in general that you want me to answer right now? No? Then we can wrap up there. And just again, I want to remind you, Monday revision lecture. If there's anything in particular you want me to address in the revision lecture, please post a reply on Piazza, and we'll do the best we can to try to answer questions.